We're going to go ahead and get started at this time. We're going to first go over the bell work, and then we'll get to today's lesson. I broke buffers up into two parts. Today, we're going to discuss the rest of the math of buffers. So there's going to be no definitions in this lesson because we did that last class, but we're going to look at a lot of calculations. So you got to get your brains ready for the day. You'll want your calculators with you. And so first thing here for the bell work, define buffer solution. Notice this time it's only worth 1 mark, but you still have to say both things. It minimizes change in pH, or any synonym for that. Change in pH. That's the first part. What's the second part? When, it has to be a specific scenario, a strong acid or a strong base or alkali are added. So when small amounts, because if it's too large, you'll destroy the buffer, of strong acid or alkali are added. And Cambridge does like to use the word alkali for base in their marks. So that's what I'm like. And then I think pretty much everyone got that point. Equations is where it starts to get a little murky. And so write equations to show how this solution, the C6H5COOH and the C6H5COO minus Na plus, how does this solution act as a buffer when named substances are added to it? And the thing is, because it says named substances, you have to write the whole thing in. You can't just put OH minus and H plus. If it says sodium hydroxide, you have to use sodium hydroxide. So sodium hydroxide is a base, right? So what would it react with? The acid part of the buffer or the base part of the buffer? Bases react with acids. So it's going to be C6H5COOH plus NaOH. And then I would do double arrows because you still have a buffer solution going on, equilibrium arrow. So now what? C6H5COO minus. H goes with OH. So Na plus is the other part. And then you would have H2O. Now, you could have written this as C6H5COONA without the minus and plus charge because it's just a standard ionic compound. But if you write one charge, you must write the other. And they gave you that guidance up here, yes. So Na isn't, it doesn't matter. They told you to write it. They said the named substances are added to it. So you had to do the full reaction with sodium hydroxide. If they just say react with acid and base, then you don't have to add the other component. But it said a specific acid or base, so you have to use that. All right, so the next one is nitric acid. And yes, you are expected to know the chemical formula for nitric acid off the top of your head. Nitric, sulfuric, and hydrochloric are the 3 you have to know. So this would be the other part of the buffer, which is the C6H5COO minus Na plus HNO3. And we have to see what does that do. So what does that make? What goes with what here? Remember that in the acid, the H is the positive part and the nitrate is the negative part. So what would go together for my products? Acid-base reactions are just standard double replacements when they look like this with the 2 compounds. You would have C6H5COO minus going with the H plus. So you would get C6H5COOH, the other component of the buffer. And then what is your other product? Na with a plus charge goes with NO3 with a minus charge, and those charges cancel, so you get NaNO3 as your other product. So this was the whole mark. Good so far? So each of these were worth 1. The next, many people did quite well on the map of this question. Happy to see that because I have given this question to Bella before in prior years, and it was more of a struggle. Ready to continue? Let's take a look. It says calculate the H plus concentration, the C6H5COH concentration, and the solution that's described, and then use the buffer formula to solve for the C6H5CO minus and plus concentration. Show your work. Leave each answer to a minimum of 3 significant figures. Cambridge is kind of nice with sig figs. They usually tell you how many they want, or you can just assume it's like 3 and not crazy. If you were taking AP Chem instead, they'd be really harsh on significant figures. You'd have to follow the initial rules I taught in pre-8 every single time. Yes, but Cambridge is kind of soft here.
If we follow those rules,
They will not count it wrong. They know the official IUPAC rules for rounding significant figures, so you can definitely follow the rules and get the answer. The guidance that I've been given is if you have correct chemistry, follow the correct official rules, you're not going to get the answers wrong. Like I said, it's kind of like a lighter thing. They're trying to help you out by telling you this is what they want. All right, so let's go ahead and solve it. How do I get the H plus concentration? Do I have information for that? I have the pH. That's all I need. For the H plus concentration, it would be 10 to the negative 4.15. So what do you get from that? 7.08 times 10 to the negative 5. So if you show that, and you write that as your answer, that's it. Yes? Any questions about this first one? We're okay with that? Okay. So then, how do I get the C6H5COOH concentration? That's what comes next. Look back at the question. Do I have information to give me the concentration of acids? I have the grams, and I have the volume. So what is the formula? Where do I start? What piece of information have I not been given that I need to solve this? I need the molar mass. I need the moles, which means I need the molar mass, right? So for the C6H5COH, the first thing I'm going to have to do, so for the concentration of C6H5COOH, before I can get that, I first have to get the moles, because I know this is got to be in moles over dm cubed, but I have grams. So if I have 1 gram of C6H5COOH, what am I supposed to do next? Divide by the molar mass. The molar mass is 122 grams per mole. That's the MR. So this would be the moles is the grams over the MR. What do you get from that? I got 0.008196. That's my moles. Is that also my concentration?
No. Yes.
Well, what we have to do there is take these moles and divide them by the decimeters cubed. Well, guess what? In the question it says it's in 1 decimeter cubed. So in this case, because that's my volume, I'm just showing the work. It is the same. And so that's why you would have seen in the mark scheme, they gave 8.20 times 10 to the negative 3 because that's 3 significant figures. It's the same thing if you had written 0.00820. You got it correct. Yes? That's part 2. So this is 2 out of 3 marks. The third mark, what do we got to do now to find the other component of the buffer? Pick a formula, right? Which one do you all want to use? You're gonna use the ASK formula? It doesn't really matter. So H plus equals acid over, you can either call it base or salt. You don't have to always call it salt, and you'll see that later in today's lesson, because it's really just the acid and the conjugate base. Sometimes it'll appear as a salt. This is a salt. Why is this a salt? Because all ionic compounds are salts. all ionic compounds are salts. Salt is not just the salt you eat. All ionic compounds are formally defined as salts. So if it's got a metal ende, non-metal, technically it's a salt. It would visibly look like crystals. That's how you would see it. So you had that last lab, actually, when you saw the last class, when you saw the little white crystals that you added, that was a salt that you were adding to make the buffer because it's got the positive and negative charges. Yes? All right. So you could say acid over salt, or you can say acid over base, which is something that's going to come up in today's lesson because sometimes it won't appear as a salt. And if it doesn't appear as a salt, you just have to remember the acid part and the base part is on there. So acid over salt times Ka. So now what do? We've got the H plus, right? So we plug in what we know, 7.08 times 10 to the negative 5. We've got the, which part, acid or salt? Acid, so we know that that's my 0.00820. I'm looking for my salt. And we have a Ka. If we don't, we're in trouble. We have the Ka right there. 6.31 times 10 to the negative 5. And then your ability to get this correct and your ability to perform algebra. So my suggestion is first to recognize that this has an invisible 1 underneath, which means that you're going to multiply these two numbers on the right-hand side. So I get 7.08 times 10 to the negative 5 equals, and then I have to multiply the two numbers. I believe, yeah, I did use the same formula. When I multiplied those two numbers, I got 5.17 times 10 to the negative 7. Tell me if you got that. When I multiplied these two numbers.
I just put my calculator.
Oh, for the final answer?
Yeah, same.
That's fine. Over salt. Then last class, I told you that if you have a formula that looks in this manner, there's literally a trick you can use that works every time you have a number and then a number over a variable. If you remember this trick, you're going to solve a lot of questions in chemistry. Like without having to do 2 steps, you can just make it 1. What is that thing I told you you could do? This. Because they're inversely proportional. You can just say salt equals 5.17 times 10 to the negative 7 divided by 7.08 times 10 to the negative 5. And then when you divide those two things, you get the final answer, which would be 7.31 times 10 to the negative 3, or 0.00731. And that's the final answer. Question, yes.
Over there.
Yeah.
It's 10 to the negative 6 instead of 9.
Let me try. 0.00820 times 6.31 times 10 to the negative 5. It's negative 7 from here. No. Divided by, let me check it again. 7.08 times 10 to the negative 5.
Yeah, I guess enough.
Yeah, I got the same thing. Nothing wrong. Okay, let me see what yours says. You're missing a 0 right here.
Oh.
You went 2 zeros in the difference. You would get error carried forward on that though, because you just missed the 0. So you get 2 out of 3 marks.
Yes.
Yes.
Why is it that when you put in the value for the acids, or
Why did I put in the value for the acid?
why do you use the second one instead of the first?
What do you mean? The formula?
No, I mean, shouldn't it be 7.08 times 10 to the negative 5 instead of the 10 to the negative 5?
For the acid? Buffer formula. This is weak acid. This is conjugate base. This is free acid in the solution. This is free acid in the solution. This is weak acid that's not dissociated. These two are not the same. Does that make sense?
Yeah.
And should it make sense that your concentration of weak acid is greater than the amount of H plus in the solution, because not all of it broke apart. That's why.
Okay.
Anybody else have a question on the lower? Yes. Yes. They're over here. Yeah. All right, so at this point, we are moving on. But as you can see, even from the bell work, there's some work to be done, right? Yeah.
Oh. Never mind, I'm so.
Maybe it'll show up again in the lesson.
No, I just realized.
Oh, okay. Unit 1, lesson 4, buffers continued, ... And so today we're going to wrap up buffers. We've actually went over most of the standard, but there is a type of more complicated math question that can show up. And so I'm going to show it to you. I'm going to show you the way that I learned it when I was both in my Gen Chem 2 class, and all of my analytical chemistry professors taught me in a specific way. And so I'm going to share that method with you. And it makes solving these types of questions easier. And so let's take a look. The objective for the day. We started this objective last class. It literally just said calculate the pH of buffer solutions in the scary, just given appropriate data. That means different things in order to get there. Yes, Etzel.
Throughout the year, are there gonna be like any other instances of only just one objective?
It happens rarely. It's rare. This is definitely one of the more math-heavy units of the entire year. Definitely. It might be the only one. I don't want to say for sure, but it's definitely one of the only days that has only one objective. All right, so what do we got to remember about buffer solutions before heading into this lesson? First, we should know our general formulas, meaning we should know that if I'm looking for moles, it's grams over molar mass. If I'm looking for concentration, it's moles over dm cubed. If I have the concentration and the dm cubed, I can literally multiply those two to get to moles. So concentration multiplied by dm cubed equals moles. This is something you're going to be using today a lot. And then what is a buffer in general? So what is considered a buffered solution? Well, we know that's the definition, but what am I looking for? I'm looking for a weak acid, and its conjugate base, right? Which we know can also be called a salt if it appears as an ionic compound. So it's a salt if it appears as an ionic compound. Appears as an ionic compound. Okay. So we know that's what a buffer is. So for example, if I saw a solution that had some HNO2 and some NO2 minus in it, this would be considered a buffer solution. The HNO2 will react with what?
Really.
React with strong base or strong alkali to make the other side. And the NO2 minus will react with strong acid to make the other side, according to Le Chatelier's principle. So because of this, the pH doesn't change dramatically, as long as I have both components of the buffer solution. All right, so that's some things going into this lesson that you need to remember. I'll pause. Before we actually get to the new stuff, there was one question in the last lesson that we didn't cover because I wanted to get to the lab and give you enough time to do that. So on the next slide, you're gonna see a question that was reprinted from last class's lesson. So let's get to it. Write equations to show how the hydrogen carbonate ion controls the pH of the blood. When you get a question like this, what you should do, it says to show how this specifically controls the pH of the blood. Meaning, how does this act as an acid and how does this act as a base? Because it actually can do both. It can be an acid and it can be a base. Wait, is there a name for a type of substance like that? A substance that could act as an acid or a base? Go ahead. Amphoteric. So this is amphoteric, meaning water is not the only thing that's amphoteric. That means it can act as an acid or a base, depending on what it's combined with. And here they want you to show this. How does HCO3 minus act as an acid to control the pH of the blood? How does it act as a base? So I'm going to put it as the acid first, and then I'll do how is it acting as a base afterwards. Act as acid, act as base. HCO3 minus. If it was to act as an acid, what would I put it with? They're not telling me a specific compound, so I would just put it with the OH minus. So what would happen? OH minus takes a hydrogen, H plus ion from this, and if it takes an H plus ion, it becomes water. And what happens to the HCO3 minus if it loses an H plus, Andrea? Yep. But it can act as an acid. It's not a great acid, but it can act as an acid because it has the H plus in it. That's how it can act as an acid, and that's what you're being asked to show. So what would it be? CO3 minus 2. So the carbonate ion. The second example, how would this act as a base? What would I put this with for it to be acting as a base? I would put it with H plus. And so this gives us H2O plus CO2. Because remember that when you make H2CO3, it always breaks apart to water and carbon dioxide. That's going to show up over and over and over again. So you need to be aware of it.
Miss, please.
Yes.
I remember from last year that aluminum oxide was amphoteric. Does that mean that it would be a buffer solution?
That's a good question because it's an ionic compound that doesn't. In the form with the hydroxide, probably yes. And because there is a form of it, like something that forms from it, that has a bunch of hydroxide. So yeah. And it would be weak because aluminum hydroxide is a weak base, not a strong one. All right, so let's take a look at this practice question. It tells us a solution that contains both Na2HPO4 and NaH2PO4 is commonly used as a buffer. I think that this presents itself maybe as a little bit confusing initially because what I read is, hey, that's a salt and that's also a salt. So what gives? But they give you the following equilibrium to help you out. H2PO4 minus goes to HPO42 minus plus H plus. And then they ask you to calculate the pH of the buffer, meaning we can choose to use one of those formulas, or you can set up the equilibrium by mixing 100 centimeters cubed of 0.5 molarity of one with 100 centimeters cubed of 0.3 molarity of the other. So the first thing, buffer solution, what formula do we want to go to?
pH equals A plus dot.
That's what we want to do?
I want. I'm about.
I see it shaking head. All right, well, you can do whichever one, right? It's going to give you the same answer. So you pick whichever one you want. What are the two formulas you have to choose from?
We'll just do it first.
You can either pick this one
I go with everyone.
or you can pick this one. And then you have to flip because it's logged inverted salt over acid instead of acid over salt. So you pick whichever one you're gonna do because the heads shaking told me overall we're gonna do this one. I'll continue using the H plus equals acid over salt times Ka formula. So let's start with that. H plus equals acid. Instead of calling it a salt, would it be more appropriate to call it a conjugate base here? Because both of these are salts and that might be confusing. So maybe we want to say acid over the base version, right? I don't know if that turns it ABK, ABK, instead of S. I don't know how that sounds. ABK. ABK. I don't know.
Gotta get in. A Burger
Is there a thing? Burger King?
A Burger King.
A Burger King? Like ABK? Maybe that will help. All right, so looking at this equilibrium, which of these is the acid variant and which of these is the base variant of the compound?
I know. Like something else.
This one is the acid, and the other one is the
Hey.
base, the conjugate base. The one with the more H's is the acid. The one with the less H's is the base, generally speaking. So that's all just to help us figure out which number goes on the top and which number goes on the bottom. Next thing, do you remember last class I said you could either use moles for this formula or molarities for this formula because they always would cancel. We've got the molarities. Do we really have to use that volume to do anything? We do not. You'd just be giving yourself more work to do for no benefit, yes.
Shouldn't we multiply times the centimeters too? Times
If you want to change the concentrations to moles, because you want to do that, sure, but it will not affect the value of the answer. Why don't you do that and come back to me and see if we get the same thing? I'm just saying, they end up being the same on the top and the bottom. The units will cancel. Whether you do the concentrations or you do the moles
also
to each
without
other.
volume.
So in this case, you ignore the volume if you like, but you don't have to. You could use the volume if you would like and change it to moles. This formula works for either. But you should notice you get the same answer regardless. All right, so then what goes on the top? Which one?
0.3.
Okay, so 0.3 goes on the top because that's the one with the more H's, the acid. And then 0.5 goes on the bottom. So at the Ka, okay, 6.2 times 10 to the negative 8. And that's going to give me the free H plus in the solution, right? That's going to give me this. Next, 0.3 divided by 0.5 multiplied by 6.2 times 10 to the negative 8. This is where I was just teaching crews how to use their calculator. This is where knowing how to use your calculator is going to really does help you out if you can plug it from your calculator like good.
Yeah.
So I get my H plus is the 3.72 times 10 to the negative 8. And is that my final answer?
No.
No, I have to take the pH. Does that mean that's 2? Here's law. Which means my answer is 7.43. All right. This is H plus times HPO42 minus over H2PO4 minus. Could we have solved this using the weak acid equilibrium equation? Question. Could we?
Oh yeah, because I have these plus.
Let's take a look. It says Ka equals these two, right? Multiplied by each other. HPO42 minus H plus over H2PO4 minus. Is this just a rearrangement to solve for H plus? Is my question to you. See if you can do that. How would you do that? these two would switch to the other side, right? You would do Ka multiplied by H2PO4 equals HPO4 minus times H plus. And then you would divide both sides by HPO4 minus. What is this? Ka times H2PO4, which is the acid over the base times Ka equals H plus. Isn't this the same thing as that?
Oh my God.
So if you have the equilibrium equation for the weak acid, you can literally just make that, and you have to, figure out how to rearrange it to solve for H plus. So algebra. As I said, the whole lesson is really just a lesson in algebra and knowing how to put your equilibrium concepts together. So if you know how to do equilibrium, technically, you don't even need this formula. Make sense? But you have to recognize what's your acid and what's your conjugate base. We'll take a look later on in today's lesson at a question where they kind of lead us into doing it that way. But we're going to continue. Ready to continue? So this was the question we had ended up with. So now, the reason why I'm taking so much time to go over this one thing today is because we need to revisit stoichiometry. Before going back to buffers now, let's review stoichiometry and specifically the concept of limiting reagents, which is something that you learned back in pre-ed. We went over very quickly in AS chemistry, but it's coming back now. And so take a look at this very, very easy example. Hi. Is it, what is it for? NHS. Okay.
So we have NHS invitations. Everyone knows what NHS is, right?
National Honor Society.
Yeah. Most of you guys are seniors and juniors, so I'm not. Ashley. Jose. Kaylee. Analia. Omar.
Yes. So finish something up, sure, while you're waiting.
Daniela. Cedar. Thomas.
So many NHS
I don't.
possibilities here.
And Tatiana.
I wasn't here.
Talk this year.
That's what-
He's gonna say anything.
Rafa, have a good day. Bye. All right. Put your letters away. Read them later. Mr. Isworthe. You're welcome.
Wait,
All right. We're gonna go ahead and continue. Good? All right, so the reason, like I said, that I'm doing this one little objective today is because I want to go back and review something really important from the past. Take a look at this. And this practice question is like super simple, but I wanted to use it to go over what we've done in the past and what can be done in the future. So, practice question. Given a mole of NaOH and 2 moles of HCl, how many moles of NaCl would you produce in the following reaction? So do you remember, and I'm going to write it over here, what is the traditional method of solving it? What did we do back in the day? Well, and if you didn't take pre-A's, then you don't know this. But what technically should we do to solve this? Go ahead.
I think you would have to find the most weighted by each of the reagents and then see which one is the limit.
Compare. Yes. It's find the moles of NaCl that each reactant will give you. Compare, find the lower amount. That's the amount of limiting reagent. Okay, let's do it. So I've got 1 mole of NaOH. That would be our given. So we put that over 1. This is what we call good old stoichiometry. And then we would say 1 mole of NaOH goes to 1 mole of NaCl. So a lot of you will be able to do this in your head. And you saw that most of the questions that we did, like in the lab last year, you were able to do this type of relationship in your head. But it's going to be 1 mole NaOH goes on the bottom. So this is called my given. 1 mole NaOH goes on the bottom. And 1 mole of NaCl goes on the top. And what we would do, and some of you just fill in the numbers and you don't write in all your units and you just know your multiplication and your division, is you divide. You cancel these out and you get 1 mole of NaCl. Do this again for the other one, the 2 moles of HCl. Over 1. And then the same ratio, right? 1 mole HCl. And I have a point here. NaCl, and you get 2 moles of NaCl. And so once you go through your stoichiometry 2 times, you all told me the next thing that you would do is you would compare. What is the lower number? So what is the lower number here between 1 and 2 moles? 1. Okay. Next question. How many moles of HCl are left at the end? 1 mole. And how did you get there?
Because okay, take 1 mole to produce 1 mole of NaCl. So if you only take 1, you're left with 1 mole.
And how do you know that? You said, what did you do to get there?
You can just subtract it. Wait, no.
That's subtracting NaCl.
Yeah, you have to find the rating.
How do we find the excess reagent? You would actually have to make another relationship, right? What I'm telling you now is there is another way besides the traditional way. So I'm going to teach you that now. Go ahead, Atzel.
If we balance the equation without using stoichiometry, will they then ask certain marks?
If you balance what equation?
Like that reaction right there.
Oh, if you solve this without using stoichiometry, would they take away marks? No, they won't take away marks for that because like I'm about to tell you, there's another way. And so what I'm going to show you now might bring back memories that might not make you happy from last year, but it's going to be something called ice.
No.
Do you remember
I love that.
an ice table? You can actually solve this using a manipulated ice table. An ice table. But we're going to call it a mole table. So remember how in ice you would have an initial, you would have a change, and you would have a final. What is our initial amount of moles of NaOH in this question? 1. What is our initial amount of moles of HCl? 2. What is our initial amount of moles of salt water?
0.
0. Reaction hasn't happened yet, right? So then we know in ice we would use C as a change. But in this case, we're reacting everything. So what reacts more, the NaOH or the HCl? Well, you're going to react to everything you have, right? So what runs out first? Can you visualize it? The NaOH. You get rid of all of it. So this would be -1. This is a 1 in front, this is a 1 in front. So this is also a -1. On the other side, what do you get? +1. +1. Do you agree? So you know at the end, you have how much NaOH left? 0. Tells you it's your limiting reagent. For HCl, you've got 2 minus 1. How much do you have left? 1. You have 1 mole of HCl, which tells you it's your excess reagent. It's what's left. And then, what do you have here? 1 mole of salt produced and 1 mole of water produced. Good so far? That is a different way of going about the same exact thing. It is going to help you for what we're about to do. It's going to make it easier. So what is this? This is a different way of going about how to figure out your limiting reagents. What you would have to use is the stoichiometry is just approached differently. Instead of having to do this whole thing with dimensional analysis, You literally just subtract what you have the least of, the limiting reagents, where you know you have to use these numbers in front to still give you your ratios. So if there was a 2, and like if this was 2 waters instead of +1, what would you have put? +2. Does that make sense? All right, so we'll try that again with this new method. Practice question. Given 1 mole of NaOH and 2 moles of HCl, really, I think this is the thing. Yeah, I somehow copied that. Let's try that again. Here's the next one. Given 0.2 moles of NaOH and 0.5 moles of HCl, how many moles of NaCl will be produced? .2 moles of NaOH, 0.5 moles of HCl. How many moles of NaCl will be produced? Try it this way. But it's not equilibrium, it's actually just final amount. So it's instead of ICE, it's IC. Because it's not equilibrium. But the same method can apply. And like I said, this is actually a method that we were told to use in all of my upper level chemistry classes. Because the other method is just too time consuming. And this gets you the answer much faster. And you still have the theory of why that works. So, NaOH would be 0.2 moles. HCl would be how many moles? 0.5 moles. Here you got 0, 0 again. Which one are you going to run out of first, NaOH or HCl? It's visible because there's a 1 in front here, right? You're going to run out of NaOH first. And so you subtract 0.2. You can't subtract 0.5 from both, otherwise you'd say you have negative amount of NaOH, and that wouldn't make any sense. So you use this up until you have no more. But these react at a 1-to-1 ratio. So this also completely reacts. Make sense? So then, here we go. Here we go. And what do we have left? This becomes 0. This becomes 0.3. And then this becomes 0.2 and 0.2. What are we doing now? It says how many moles of NaCl have been produced? Do we have the answer? 0.2. If I had the volume, could I ask you at the end of this what your pH of the solution was? So if I had given you a volume, I didn't here, but if I'd given you a volume, could I have then asked what the pH of the solution is? Yeah, because I have leftover strong acid. And that leftover strong acid will dominate what the pH is, yes. That's the only thing that'll matter because salt water is not going to visibly affect your pH much. The presence of strong acid will predominate what your pH is. These ideas I'm bringing up because we're about to see it in our current curriculum. Yes, Francesca.
So the moles for HCl, since it's 1-to-1 ratio, for H would just be 0.3, right?
Yeah.
And then if you gave us the like volume analysis for H, I know pH, you would just get the H from.
And then you have to divide by the, well, this would be the H plus. This is also your H plus because it's a strong acid. So if I gave you the volume, you would just divide that moles by the volume in dm cubed.
And
That would
then-
give you H plus, and then you take the negative log. So it works. Why am I bringing that up? Well, we're going back to vapors. So this whole new approach to stoichiometry that I'm showing you is to help you reason out the following questions you're about to see. And so going back to where we were, and by the way, this is what we worked with last class, right? In the actual lab, we worked with ethanoate and sodium ethanoate. You've still got the same information here. So remember that instead of salt, what could we call that instead? That can be called conjugate base. It's a salt if it appears. Like here, it doesn't appear as a salt, does it? Like in this equation, I don't see a salt. Do you? So what would be the salt technically? in this equation. Because the spectator ion is missing.
H2CO.
This is technically the salt or the conjugate base. Because like I said in the lab we just did, we saw it as sodium ethanoate. The sodium was there. And then this is the acid, the weak acid. Okay. So, Henderson-Hasselbalch equation is this one. Your one choice, your other choice is the AB formula. Acid over salt times Ka or acid over base times Ka. Whichever way you want to remember it, technically you should view it as both. Because sometimes you'll see it as a salt and sometimes you'll see it as the conjugate base. It's the same thing, it's just the frame of how they present the question to you is what could make it confusing. So, you can make a buffer a different way than what we did last class in the lab. Last class in the lab, I literally gave you some of this, right, in a solution, and I gave you some of this with the sodium, and it was crystals, right? And you mixed them together and you said, boom, buffer. There's another way to make a buffer. The other way is to start with the weak acid and to add a base to it, a strong base to it. So like, let's say you had this CH3COOH and you added NaOH to it. What would be your products?
H2CO, Na.
H3COO, Na, and the other?
H2O.
H2O. Okay. So if I add a strong base to a weak acid, as long as I have more weak acid than that strong base, then what? I'll make some of this and be left with some of that. What do I mean? Let's say that I had 0.1 moles of this and 0.01 moles of that to start with. Which would run out first, the NaOH or the CH3COOH? The NaOH. And so using what I showed you, if I subtract 0.01 and 0.01 here, what am I going to add to the other side? The same numbers, right? 0.01 and 0.01 moles of all of these. So this will be gone. And we'll have 0.99 moles of this. And we'll have 0.01 moles of that. And we have some weak acid and some of its salt, which means we have a buffer. So what I'm telling you is that one way to make a buffer is to take a weak acid and to combine it with a strong base, as long as you have less strong base than the weak acid, and it'll make the other part of the buffer. And so that's how you can make a buffer. And this is the other type of question we're going to encounter in your math questions, your homework questions that you have. Yes? All right, so this is what you're going to do. If this situation comes up, and I'm going to show you in practice examples, I have up to 3 we can do. Step 1, we're going to create a chemical equation, even if they don't tell you to, unless you can do it without creating the chemical equation. So we're going to create a chemical equation between your weak acid base provided and the strong acid base that they're adding. So you've got to know your strong acids and strong bases by heart, right? Determine how many moles react. You choose how you want to do that. If you want to go the traditional method and do stoichiometry, feel free. I'm now going to show you with the new method because it is easier once you understand it. And this is going to be the amount of moles of strong acid or strong base added unless the strong acid or strong base is in excess. And if it is in excess, then you don't have a buffer. It won't be a buffer. It'd be something else. And then it says use the final mole of both your weak acid and your conjugate base. Plug into one of your buffer equations. You find your pH from there. And so let's take a look. And I have 3 paper 4 questions for you. They each have 2 parts. You'll notice that the rest of the slides are just examples of what I've been going over here. So, question 1. You've got some. They wrote it differently, HOBR, but that's H-bro. H-bro. HOBR, bromic acid, is the weak acid. Its Ka is given to you. Can you calculate the pH of just the weak acid? What would we do? This is weak acid. They asked us to calculate pH. Where do we go with this? Do we have a formula? Formula for weak acid. What lesson did we learn that in? Lesson 2. I got a weak acid. You can either do it by setting up an equilibrium, or you can just remember the formula. If I set up the equilibrium, it's HOBR goes to H plus OBR minus. That's the equilibrium. So the formula is just the equilibrium equation, right? It's Ka equals products over reactants. Products are this times that. Over what? Over HOBR, but you could have alternatively just done or Ka equals x squared over hx. If you just remember the basic formula for it, it works. Do you remember this? This always works for weak acids. So what do I have the information for? I've got the Ka. What else do I got? Got the weak acid. What am I solving for? pH. So what in here am I solving for? What gets me to pH? H plus, right? So x squared, right? But if I remember those two are equal to each other, so if I'm solving for one of them, I can call them both x, the same. So then now I'm going to solve for x. So I multiply both sides by 0.2. I have to do my algebra thing. And then I get, flip my paper. I get the 4 times 10 to the negative 10. If you wonder why I solve all the math in advance, it's because I don't trust my brain in the morning. So I do it the night before, because trying to get up and running. 4 times 10 to the negative 10 equals x squared. What do I do now? Square root. And then I get 2 times 10 to the negative 5 equals x, which is h plus. What do I do now? Take the negative log of that. And my pH is 4.7. That's my pH of my weak acid. That was the first question. That wasn't what we had for new stuff yet. Now, next slide, we'll have the new type of question. Yes.
Just to make sure, the H plus and like the base is always the same.
In a weak acid, yes. Because what's happening here is that, let's say this is 0.2, right? That's what I was going over in that lesson. This is going to be minus x. We don't know what that x is because not all of the HOBR reacts, right? So this is traditional ice table. So this is 0 plus 0, 0 and 0, and this is plus x and plus x. So because both of these are the same, they're both x. Make sense? That's why. It's because it's an equilibrium. And remember that x don't matter. X's that are added and subtracted to other numbers, they don't matter, which is why we just see 0.20 here, not 0.20 minus x. If you had to keep it as 0.20 minus x, you would not like the math as much because it would turn into a quadratic equation and you would have to solve the quadratic equation. But in all the questions in this course, you can assume x is small. Which is good for you. Continue. Okay, so here it is. Here we go. This is the new question. New. question. Hi. As approached. Here it is. New question type. 5 centimeters cubed of a 0.2 molarity potassium hydroxide was added to 20 centimeters cubed of a 0.2 molarity HOBr. And they want us to calculate the pH of this buffer solution that is made from adding this strong base to this weak acid. So what are the steps? What did I say we should do? First thing I suggest is create a chemical equation. Create a chemical equation. Which means it's HOBr plus KOH. You could write them in either order. What'd that make? What are my products? Water's one of them. And it's, okay, so I would underline this just to make sure you put the right atoms together. K's got to go with OBr. So it's KOBr plus H2O. So far, so good? All right, what's the next thing? What did I say? Make sure I chart. Determine how many moles react. Determine how many moles react, which would be the chart. But in order to know how many moles react, I have to know how many moles I have. Am I given moles here? Am I directly given moles? No. Am I given a pathway to get to moles? Yes. For both compounds, I'm given the volume and the concentration. When we react moles, we must react in moles, not equilibrium, because we're actually figuring out how much reacted. This is stoichiometry. We must react in moles because it's a mole table. It's not an ice table. You're not going to leave it in concentration. You have to change it to moles because you're figuring out the stoichiometry. So then I'm going to, on the side, I'm going to find the moles of, I'll do KOH first. KOH. What's the way to do that if I've got volume and concentration? That's why I wrote it down earlier. If you remember, back at the beginning, we said concentration is defined as moles over dm cubed. So if what I'm always going to be solving for is moles, this really just means I'm going to take my concentration and multiply by the dm cubed. Are we okay with that? So I'm going to write concentration times dm cubed equals moles. Are we good with that? Just making sure that's okay. So I'm going to do concentration times dm cubed is moles for each one, right? It's just one calculation. What's my concentration for KOH? 0.2. What's my concentration for dm cubed? I have to move this over 3 spots, right? So I have to remember that that's going to be 0.005. And so to do your math correctly, I get 0.001. Check if you get the same. Be careful when you have so many zeros, you may get confused. So it does happen. Even I'll miswrite a 0 here and there, which is why I said I usually solve my questions the night before, because I'm more likely to be with it and not miss a 0. Learn your rhythm, what works for you. Some of us are morning people, some of us are not. All right, are we okay with 0.001 for the moles of KOH? Okay, but that's not the only thing we have to find the moles of. What else do we have to find the moles of? We have to find the moles of HOBr, right? So you're noticing I'm doing that on the side because I'm going to bring that into the table afterwards. So find moles HOBr, same formula. Moles is concentration times dm cubed. Concentration is 0.2. dm cubed is 0.020. And I had gotten 0.004. Good? Okay, so now that we have the moles of each, we can now go into here. I have my initial moles, the amount that react, and then my final amount. My initial moles of HOBr are 0.004 and KOH is 0.001, and I have nothing of the other stuff. What runs out first? And because the numbers, and in all acid-base reactions, I think I told you this, in all acid-base reactions, your numbers are easy, aren't they? For stoichiometry, because it's 1 and 1. You may get a 2 somewhere, maybe. But most of the time, it's all 1s. So that's what makes the math so easy to do. So which one runs out first? Visually, can you see the difference between 0.004 and 0.001 and see which one you're going to get rid of?
0.001.
That's the limiting reagent, right? So KOH is the limiting reagent here. That's minus 0.001, minus 0.001. On the other side, it's plus 0.001 and plus 0.001. And then you figure out what you have left after reacting this weak acid with this strong base. Yes. To the bathroom? Stand showing up.
Did you get the box?
You can grab the pass, but you have to do the phone thing. You don't have the phone?
It doesn't work.
Then I have to write you a physical pass.
It'll take just a moment, don't worry. Today is the 30th? 28th, 29th? Thank you, Axel. What? It's been a long week.
In a long week. I don't know what day it is. I just know it's Friday. So that becomes 0. Do you agree? No more strong base. What's left? 0.0603 moles of weak acid. And what else is left? 0.001 moles of its salt, right? And then 0.001 moles of water, which you can not care about because that's water and all solutions have water. So the water is going to be negligible. So water not included in the calculation. The fact that you made 0.001 or moles of water does not matter. You should point that out for yourself so you don't get confused when you're doing any homework and you see, oh, but there's a number there. Should I be using that? No, you should not. All right, so what we have left at the end of this reaction between the weak acid and strong base is weak acid. And what is this? What is this? It's salt. That's its conjugate base. That means they gave you, and I highlighted it because I was looking for buffer questions. So that's my, forgot to take the highlight off. Looking for old buffer Cambridge questions. But buffer.
Control F.
Control F. That's what that is. Now what do? We have the steps here. So what does it say we do next? Use the final moles of the weak acid in your conjugate base form and plug into your chosen buffer equation. You know, if you want to do pH equals pKa, you could do that. If you want to do H plus, you could do that. So this was step 1. This was step 2, right? And so what's step 3? I'm moving over for step 3. We're now going to find the pH of the buffer. You can see why I printed these out 2 per slide now. That's another clue. If you see 2 per slide, that means that the math is more involved, is what it is. There's more to do. Okay, I'm going to use the H plus formula because that's what you all voted for unofficially. A plus equals acid over, you want to do ABK or ASK? ABK? ASK? Doesn't matter. Pick one. Cambridge would accept them both. I see mark schemes where they do acid over base and other ones that they do acid over salt. That means you could use either. Now what? I want pH. I think I'm looking for H plus. I must have my acid and my salt. Okay, wait. But these are in moles. Do I have to go back and change them to concentrations? Do I?
So,
No, I do not. Why? Because moles on the top, moles on the bottom, those units cancel. That's why I told you that last class. Because the units, as long as they're the same, you're looking for the ratio between your acid and your salt. So you do not have to change these back to concentrations. You can plug in the numbers as is. Good with that? So this becomes, to solve, 0.003 over 0.001. What's my Ka?
Mm.
Well, this was a continuation question, right?
Oh,
From this one.
2 times 10.
So this is the same thing. So it's 2 times 10 to the negative 9. Because you know how that's how Cambridge questions are. There's a B1 and a B2 and a B3 and then a B4 and then a, you know, it goes on. And then a C1 and a C2. This is all the same question.
1C5.
1CIV. I see like all kinds of things. All right, 2 times 10 to the negative 9. Now what? Now we do multiply by. I get 2.1 times 10 to the negative 8. See if you get the same. I might have entered it wrong. I did enter it wrong. Yeah, my brain don't work in the morning. Last night I wrote 6 times 10 to the negative 9. Does that sound better?
Yes.
I wrote a 7 instead of a 2. Those are my brain don't work if I try to do something in the first step of the day. That's math wise. I'll punch in the wrong number in my calculator. 5 times out of 10. All right, so did you get 6 times 10 to the negative 9? Great plus. Now take the negative log of that. That's the H plus. Take the negative log. And you get 3 significant figures. 8.22. Can't read my handwriting.
It wasn't 6, right?
No. It was not. Can't read my handwriting, but 8.22. Are we okay with this? No? Oh, you just missed some. Yes.
Yeah.
You're good? Got it? I think going over this one time is not enough. That's why you saw that I have another example. Another one. You know, the crazy thing, how many marks is this worth? 2. That's worth a good old 2 marks. Also worth a good old 2 marks. Throwing it out there. Seems a little heavy. I mean, a little light for the amount of work you're doing. Just throwing that out there. That'll happen again in this class later. But then you'll have a question like, identify this bond angle. And you have to write that it's 109.5 degrees, and that's also a mark.
Wait, we're still gonna get questions like that?
Yes. When we get to transition metals. When we learn about ligands, which some for some reason. December, we do bond angles again. We get Lewis structures and all that good stuff.
Is there anything from last year that isn't gonna come back?
The summer packet I gave you had some pretty good guidance on the topics that you would likely see again. What?
I lost it.
She posted it.
It is online. There's a copy online. But it does have pretty good guidance on the topics that are revisited. But most topics do at least sort of show up again. Okay, paper 4, question 2, meaning that this is literally me trying to give you more of the same type of questions so that we can revisit these steps again. This one. They give you the value of Ka is butanoic acid is 1.51 times 10 to the negative 5 at 298 Kelvin. Does 298 Kelvin matter?
No.
Yes and no, right? If the temperature was different, this value would be different as well because K is affected by temperature. But they're just telling you this is the standard, right? So calculate the pH at this temperature, show your work. What is it? What do we do? This is what? What is this? Is it a strong acid? A weak acid, a buffer, what is it? Because what it is tells me what to do. It's a weak acid. It's got a Ka. There's no salt mentioned, right? It's a weak acid. So what's the strategy? So you got to go to what it is, and then it's the strategy. Which, do we have to write the equilibrium balance? No, we could just do this. Yes? You don't have to write the equilibrium balance if you know what to do. The equilibrium helps understand why this is what we do, but that's what we do. So Ka is 1.51 times 10 to the negative 5 equals, I'm looking for x, and what goes on the bottom? 0.1, because this is the hx, right? The x is all that stuff. That's why it's powerful to just say, oh, that's all just hx, instead of having to write out everything. When you're not being asked to, you're just being asked to do the math. So then now what do? We solve for x. So that means multiply both sides. Same math as before. I 0.1, rinse, wash, repeat. The same thing. Same strategy. I get, man, I was lazy here. I skipped steps and just took final answer and calculator. If any of you do that as well. I get 1.51 times 10 to the negative 6 equals x squared. I take the square root of that, just so you can follow along. X equals 0.001228, or its equivalent in scientific notation. Is that the final answer? No, it is not. We take the negative log. pH is 2.91. We good so far? Some of you are working on beating me to the answer. Appreciate that. You've got the strategy. Continue. Okay, the next question is related again. Same type of question. 5 centimeters cubed of a 0.1 molarity NaOH is added to 10 centimeters cubed of a 0.1 molarity CH3, CH2, CH2, COH. What's the pH? So what's the strategy? What's going on? We've got a strong base being added to a weak acid. Why would we be doing that? What does that do? It makes a buffer. So if I put it, remember, a strong base plus a weak acid is going to make a buffer as long as your strong base runs out first. So this is one of those things I'm saying, you have to look at what you have to tell you what to do. This question's a little bit more difficult than the last one in that they didn't tell you you were making a buffer. You had to get that yourself. Just from the fact you are reacting a strong base with a weak acid. So let's go through the steps. What's step 1? Get the chemical equations so that you can make your little chart. Chemical equation is NaOH, or you can go this way, C3, CH2, CH2. Cambridge is not letting you forget about organic. No, they're still including organic molecules in your questions. It's gonna come back. It'll always come back. Organic will come back. It's just looming.
No, organic's the best.
Looming. It's coming back. What do we do now?
You got the most of all.
Well, I gotta finish the equation, right? I just wrote out what they gave me. So what are my products? H goes with OH, water, and your other product is? Ona. Oh, we remember that. Do you remember Ona? Huna. Huna's going on here. Just a double replacement reaction. got our equation. What came next? This is supposed to be what we use to do this, but we can't do this if we don't have moles. So we have to go get moles. So now we have to find moles. That's what I'm doing on the side of each. I'm gonna do NaOH first. What's the mass for that? You remember from the last one? Multiply, right? 0.1 times 0.005. I get 0.0005. Don't miss a zero. Find moles of butyric acid. Just me making sure it's labeled correctly. Moles is 0.1 times 0.010. I think it's 0.001. That's my brain's warning. May not be correct, but I've been doing this. All right, so what now? Plug in here. 0.001, 0.000500. Which one's less?
0.004.
This one. Do you agree that that's the smaller number because it's got one more zero in it?
Yeah.
So subtract the smaller number. Minus 0.0005 minus 0.0005. On the other side, plus 0.0005. And literally it's the same thing for water, but we don't care. Right? Just water. It's always there. It's not going to affect your math.
When the point zeros. Oh, never mind. I misread that wrong. I'm sorry.
It happens. Goodbye, strong base. Goodbye. There's zero of that. That's the limiting reagent. So what's left? Subtract these two numbers, you get 0.005. Add to here 0.005. You have left weak acid and its salt. And you can go then proceed to pick your formula to use. We're just going to keep using the same one. However, if you remember, if you use Henderson-Hasselbalch, this is a unique situation. Because your weak acid and your salt are the same, they will cancel out. And if you use the Henderson-Hasselbalch, the pH will directly equal the pKa. So if you were to choose to use this one, because these two amounts are the same, that whole thing cancels out. And your pH would literally just be the pKa. If you continue, I'm just going to keep showing using the same formula for those of us who like to use that H plus formula. It would still be 0.005 over 0.005 times Ka, which is, where's my K? It's that, 1.51 times 10 to the negative 5. You still see that these amounts will cancel. So H plus is just equal to that. And so if you take the negative log, what does that give us? pH is, I get 4.82. See if you get the same. Does that make sense? I'm going to pause, ask if it makes sense. And then let's take a look at something before we do the last question. Look at the first answer for the first part. You had a weak acid. What was that pH? 2.91. You added strong base to that weak acid. You made a buffer. What is the pH now? Does it make sense? First of all, I added a strong base that the pH went up. Does it also make sense that the pH of the buffer is similar to the exponent of the Ka? So it all like mathematically, it checks out from ideas that we know. Because remember, if we've got a buffer, the actual pH should actually be similar to the exponent of the Ka, but in a positive value instead of negative. Yeah? Okay, so you can verify whether you're on the right track. So if you had gotten a pH of like, I don't know, 12.3, what would you say about your work? There's definitely something wrong with that. That's definitely not the answer. we done goofed somewhere, right? Okay, last question. So this question I wanted to bring up because I thought it was unique how they had you solve it and they lead you to how they have you solve it. So this is question 3. First question, what is the acid dissociation constant expression for ammonium? What would we do? If I want the expression, what do I have to do? That's not math.
Isn't that the formula?
That's products over
Yeah.
reactants. How do I get that? For ammonium. NH4 plus. How would that dissociate?
NH3 plus NH.
NH3 plus H plus. So then what is the expression?
NH3 plus H over.
Products over reactants. Good so far? That's it. That's all that is. Products over reactants, but for the expression, you must include the identities of what you have. If you write for expression products over reactants, like that's your answer, you're not going to get the mark because they want it specifically for this substance. All right, next. How do we write equations describing how these two components act as a buffer? What do we have to do here? Do you remember from last class? For one, we add H plus, and the other we add OH minus. Because they didn't tell us what compound, so we could just do H plus and OH minus. So H plus would react with which part of the buffer? What do you think? The NH3. So it's NH3 plus H plus goes to NH4 plus. That's the first equation. That will give me 1 out of 2 marks. Which side do I add OH minus to?
Yeah.
So now I write NH4 plus OH minus, and what does that make me?
NH3.
NH3 plus H plus. That's that. Good. Oh, so that was 2 marks. That was 2 marks. Just a reminder. That's also 2 marks. Friendly reminder. All right, let's take a look at this question. It says, and I think this is the last one, right? Yeah. Numerical value of Ka is 5.6 times 10 to the negative 10. They give you a buffer solution prepared by taking ammonia and adding it to hydrochloric acid. And they ask you to calculate the pH of the buffer for. What should we do now? Write chemical equation. Because they have given us a method to create a buffer by taking a weak base, actually, gross, and adding a strong acid. So we're going to start with the equation. Write the equation. By the way, I believe that I made this one of the homework questions for part 4. I'm pretty sure. Therefore, I'm literally giving you the answer if that's true, and that's on purpose because I figured people would get confused. So I'm going to go ahead and just inform you that you either have a question just like this or maybe even the same exact one in your homework. I looked over it when I was making the answer key. All right, write equation. So the equation is NH3 plus HCl becomes what? NH4Cl. Now what? Find the moles, right? Then I have to find the moles. So find the mole of each using concentration equals moles over decimeter cubed, but we just multiply. So for NH3, what would that be? Multiply these two. This is already in decimeters cubed, so you don't have to change it. So it's 0, it's moles is concentration times cm cubed, right? Just write it until you remember what to do. Concentration is 0.25. DM cubed is 0.80. That number is. I got 0.20. See if you got the same. 0.20 for NH3. Do the same thing for HCl. HCl moles is 0.2 times 0.2. And I believe that's 0.04. 0.04. You see what's gonna run out first, just by looking at the numbers. HCl. So ICl. NH3, 0.20. HCl, 0.04. 0. Now what? Subtract the limiting reagents. Limiting reagents, we can visibly see it's a smaller number. So this would be and that's where we're at now. So now what do we do? Now what do we do?
And now you gotta take
Figure out the formula, right? So you can use this to solve. That's what they're telling you. You can use this to solve because you've got the NH3, you've got the NH4 plus, and you've got the Ka. So they're telling you that you could use that formula to solve. You could either use that formula to solve, or what else could you use to find the pH of the buffer? Ramon.
The one with the logs.
Logs,
The one with the
or
logs.
just ask, right? Just, acid over salt times Ka. So what are we going to choose? Let's try the one that they're telling us, which is this one, right? Ka is NH3 times H plus over NH4 plus. What would that look like? What'd you get? NH3 is 0.16.
Miss, how you know they can stop using that one?
You can always solve using that one.
Oh.
So NH3 would be 0.16. NH4 would be 0.04. NH plus would be, what am I looking for? H plus, right? And what would be my Ka? 5.6 times 10 to the negative 10. What do we do after that? 5.6 times 10 to the negative 10 equals, that's 0.16 divided by 0.04, so you can just divide those two numbers. What are those two numbers divided to become? That's, I get 4. Oh. 4 times 8 plus. Divide both sides by 4. I get 1.4 times 10 to the negative 10 equals H plus, and take the negative log. What's the negative log of that? 9.85. So with whatever method you chose, and technically there's 3, whichever method you chose, the final answer in the mark scheme was 9.85. You may ask, does Cambridge care which method we choose? No. You can pick whichever formula you wish to choose. You can either use Henderson-Hasselbalch, you can use the ASK formula, or you could literally just make the equilibrium equation and solve it from there, which is what we did. That's what they kind of leaded you to what they wanted you to do here. So I wanted to show you those methods. Kind of makes sense? You have homework. To give you some extra time, on this one, because I know that this math was harder. I did give you this question, and also I'm giving you an extra couple days. So you'll notice that I put the homework for this one due next Friday. That gives you time to ask questions on Wednesday. Next week tutoring is on Wednesday. Next week tutoring is on Wednesday because there's no school on Monday. Alrighty, we did it. We got through it. So we take a 5-minute brain break.
Yeah.
That's a 2-hour brain break.
Yeah, but I didn't do the contest because I did today now.
That's a 2-hour.
Look, hold that.
Yeah, I know.
Nothing. Like, oh, okay.
You don't want to back through?
Also, don't forget the lab fees have just posted on OSP. Remember, there's a $10 lab fee. They're up until the 21st of December.
Yeah, I love payment fees. I love paying fees.
You love paying fees.
Yeah, well, tough.
Thank you, Preston. Thank you, Sophia.
You can talk to them.
I still have to learn.
You can talk to them. Like, part.
I do not know everything.
I know just about Phoenix and William, that's not it.
William is.
Yeah.
And he knows a lot.
If you finish everything else.
Like, it's good idea.
Francesca, when?
It's fine.
So the teacher is coming to class, and I was like, wait a second.
Yeah, listen, listen.
I was sat there for a while.
I know you're really sad about your like disgusting
Bro.
green paper. But like you don't have to like steal my yellow paper. Like
Instagram post.
Yeah, my mom's not.
That's pretty. Alright.
Hey, that's not mine. Too bad.
No, Caesar, you said your name was Batman. When you made your tag that you didn't mean to make. What happened? Why does it look like this? Okay, stop.